Welcome back. Now we're going to start looking at systems of first order linear ordinary differential equations. So why do we want to look at this? Well, this is actually a very, very important topic in all of physics and engineering, because this is how you represent or solve more complex systems. So, like, for example, there's a lot of physical problems. Pretty much, probably all physical problems have a number of separate but interconnected components, right? So, like, you'll have problems that involve several dependent variables. So, like, an example of this: imagine holding a ball that's connected to a string. You're holding the string, right? The ball's hanging off the string. You apply, let's say, a force to the ball, and the ball starts the ball starts swinging, right, back and forth like a pendulum. This pendulum is going to have an angular rate. It's going to have an acceleration. It's going to have a velocity. It's going to actually have, I guess, two components. I don't know. But you get the idea. It's going to have multiple dependent variables. What you do with these dependent variables is you solve for something called the equations of motion. These equations of motion are usually always second order. The equations relating to physics are almost always second order because of the fundamental laws of our universe. Specifically, how force relates to motion. F equals ma. Where acceleration is the second derivative of position. So the equations of motion, or any physical system, naturally becomes second order. That's what allows for the object's change of inertia and momentum. Anyways, that's enough physics talk. But I will say, though, if you are dealing with those kind of systems, they typically call this, well, let me explain this first. So what you do with the EOMs is you convert it into a system that you take the second order equation and you convert it into a system of first order ODEs, linear ODEs. It's very important, linear. We'll get into nonlinear stuff later. What you can then do with these systems now is because say, for example, you had an equation of motion for position, and in that position term you're going to have like an x prime, right? Like, say x's position, it's going to be second derivative in there. In order to analyze the say the velocity and the position, you need to convert it into a system of first order linear ODEs. One's ODE would represent, say, for example, the velocity. The other one would represent the position, right? Specifically, you convert them into very fundamental equations, which is very helpful in EOMs, because it helps you determine everything about the system. If you study control systems, this is how you get the transfer function of the system. This is how you can determine the stability of the system, to design your control system, to control the system. Stability we will actually get into in the next chapter, but I just wanted to give a little brief overview of why we want to look at this stuff. So typically what they call it in, I guess, non-mathematic terms, it's called state space. This is converting a system or your equations of motion or whatever that you have into state space for representation. This is what's needed to solve these problems numerically as well. In order to solve, say you have a second order ODE, right? This is another thing. This is another reason why you want to convert it to a system of first order linear ODEs. If you have, like, for example, second order ODE, you cannot solve that numerically via code. You need to break it up into its first order linear ODEs and apply an algorithm that can solve it numerically. I'm not going to cover that probably on this channel. I might later. But there's like the Euler method, I think it's called. It's been a while since I did that stuff. But yeah, anyways, so that's another reason why. So now I gave you 2 reasons why. I'm sure there's plenty more reasons why you'd want to do this. But let's get into it. So the first things first. So when you're first looking at these, systems of first order linear equations, we're going to first look at how to actually convert a second order equation into first order. So no better way to do that than to look at some examples. Now this first 3 here, they're homogeneous, as you can see. The equations are equal to 0, right? Now keep in mind, this whole chapter here is based on the same pretenses that we use in second order ODEs when we have constant coefficients. So all of the differential equations will have constant coefficients for linear differential equations. Okay, so let me look at my solutions here. I have them all written out on paper. Okay, so for this first one here, we have a second order differential equation, linear with constant coefficients. So what we want to do for number 1 here, we want to call, so we have u double prime, u prime, and u. What we can first do is we can set x, let's call this x1, and we're going to set it equal to u, okay? And then we also can set x2 equal to u prime. What does this do? Well, if you look at this, the derivative of x1 would be u1, I'm sorry, not u1, but u prime, right? So if we take the derivative of x1, obviously this is with respect to u here, this would be u prime. U prime is equal to x2. So that tells us that x1 prime is equal to x2, right? Knowing this information, we can solve for x2 prime. Well, x2 prime is equal to u double prime, right? So we plug what we know into number 1 into this first equation here. So we have u double prime, which is x2 prime, plus 0.5 u prime, which is x2, plus 2u, that's x1. And that is equal to 0. And that's it, we're done. So our 2 equations are x1 prime equals x2, and the other one would be x2 prime is equal to negative 0.5. I'm just rearranging this equation. x2 minus 2x1. And that's the answer to this one. See, pretty simple, pretty straightforward. Let's take a look at number 2. Let me move down a page. Number 2, it's a little bit different, right? We have a t squared in front there. we start with the same thing here, so we can set x1 equal to u, set x2 equal to u prime. Same thing here, we know that x1 prime is equal to x2 prime for the exact same reason as before, because x1 prime is equal to u prime, which is equal to x2. We know that x2 prime is equal to u double prime, just like before. We now can plug these in here. Yeah, so we have x2 prime plus 0.5 x2 plus 2x1 equals 0. Oh, I'm looking at the wrong one. I looked at number 1. Sorry, t squared times x2 prime plus t x2 plus t squared minus 0.25 times x1 equals 0. And that's it. So if you want to actually, write this in the proper form, you need to solve for x2 prime. So x2 prime would be equal to negative, let me think, negative x2, right, over 2 over t. Let me think, because you move that over, you divide it by t squared, that becomes, yeah. And then you have plus t squared minus 0.2. I'm just going to leave it like this, over t squared. You can separate that up, but it's the same thing. That would be times x1. Would that be minus? Yeah, that would be minus. Okay. And then the other equation was just x1 prime equals x2. So that's the two EOM. I mean, not EOMs, but I'm still stuck on my dynamics talk. These are our two first order linear ODEs. Now number 3 here. Sorry if I'm talking kind of fast here. Number 3 is interesting. We have a fourth order ODE, right? So what we would do for this case is we just define more x's. So you define as many x's as there are per system parameter, right? So we have 1, 2, 3, and 4. x1 would be u. We just keep going right down the list. U prime, u double prime, u triple prime. Remember, you exclude the last one. Excluding the last one allows you to rewrite it in terms of one lower order, right? So for this one's a little bit more interesting, right? We know that x1 prime, looking at these two, x1 prime is equal to x2. Looking at these two, x2 prime is equal to x3. Looking at these two, x3 prime is equal to x4. So there's our first first 3 ODEs. Now we need the last one yet. So we look at our equation. We plug in x, because remember x4 prime is equal to u to the 4th. So that's x4 prime minus u, which is x1, equals 0. So these right here are the 4 ODEs in the system. This is, just a case. Physically, this really wouldn't happen usually when you have a fourth order. But it's cool to see that you could do it still. Okay, now we have some new stuff going on. Let me scroll down here. Yes, so we have this, let's do 4 and 5 first. We have some non-homogeneous ODEs. Here, let me do this quick. Sorry about that. Okay, look at number 4. So this is non-homogeneous. We have, on the right side it's non-zero. In order to solve this, we would have to have initial conditions. Oh, 5 doesn't even have numbers. Interesting. These are also pretty straightforward. Don't take very long. So number 4. So you can see we're given initial conditions. So the way you do this is I guess we start with the same thing, yeah. So we call x1 u again. We only have 2 variables needed. this is the same exact thing again. X1 prime is equal to x2, just like before, because you know, x1 prime is equal to u prime, which is equal to x2. Now we have let's rewrite our initial conditions actually. Before we do this, we can rewrite our initial conditions. This means this is x1 of 0 is equal to 1, and x2 oh yeah, x2 of 0 is equal to negative 2, right? So those are those initial conditions right there. Those are our rewritten initial conditions. So we rewrote the initial conditions. This is part of the solution. Now we need the equations. So here's our first one. Now we just need the second one. We have x. This is very simple. X. This is the same. You do the same exact thing. There's nothing special about it being homogeneous. Just yet rewriting the initial conditions, I guess. This is also, as you can see, very simple. X2 is equal to u double, so x2 prime plus 0.25 u prime x2 plus 4x1, that's u, is equal to 2 cosine of 3t. Right? Yeah. So, here's our two ODEs and our two initial conditions. Obviously, this initial condition will correspond to this one, and this one will correspond to this one when you're solving it. Okay, number 5. So, same exact thing. x1 is u, x2 is u prime. Let me zoom out. Let's rewrite the initial conditions. x1 of 0 is u naught. x2 of 0 is u naught prime. Same thing again, x1 prime is equal to x2. Now solve the other one. So we have x2 prime plus p of t. This is literally the exact same problem, just without numbers. Plus p of t times u prime x2 plus 4, no, sorry, look at the wrong one, q t times u x1 is equal to g of t. This is just like a general thing. And then, you know, this is the answer right here. This one, this initial condition is for that one. This one's for this one. Alright, that's it for, I guess, non-homogeneous. It's pretty much the same idea. That's gonna bother me. Hold on. Oh boy. Never mind, it's staying like that. Okay. We have number 6 now. This is, we're now gonna do the opposite. We're now going to convert back into second order from a system. So it gives us the whole layout here. So these problems are a little bit longer because now we're actually going to solve the differential equations for their general solution. Right? So let me open this up here. Now, there's an interesting thing about this that I want you to keep in mind. When you solve a system of ODEs, you can solve it by keeping it in its form like this and solving for what's called the eigenvalues and eigenvectors. You might have experiences with this, you might not. But don't worry about it in this video. I'll cover that in a little bit. But that is one way you can solve it. The other way that you could solve for this is you just solve for the general solution of the ODE, just how we've always done them, right? So remember, there's two ways. So two ways. I'll write this down. I'll say method 1 here. Solving for each separate general solution. For this problem, it would be x1 and x2. The second method would be to solve the system, or the given system, I should say, for eigenvectors does that give you the general solution? Let me take a look. Eigenvectors. Oh, and eigenvalues. For eigenvalues. Okay, I remember now, yeah. Eigenvalues and eigenvectors. To get the same answer. Now this method is typically a little bit easier. I guess it does depend, but we do this later. Before we do that stuff, after this video, I'm going to go over some basic matrix operations like addition of matrices, subtraction. This might be review, and then I'll do, I believe right from there I'll go into, actually, and I'll probably do a video on matrix row reduction first. Reducing to an upper, just solving, reducing a matrix to solve for the variables. And then, I guess we have to look at determinants as well. Maybe I'll do that in the same video, but I'll go over all that stuff because we need all that before we can do the eigenvalues and eigenvectors. It requires a little bit more pain to understand, but the gain is worth it, But for right now, we're just going to look at method 1. Solve for each separate general solution x1 and x2. You should be very familiar from this, from first order ODEs, right? Let me find my solution so I don't get it wrong. Okay. First things first. How do we do this for a system? For a system, right? Well, we can start with some substitution, right? So we can substitute in. I'm going to take the first equation here. I'm going to just follow what I did on my solution here. And I'm going to rewrite it for x2. Correct? Once we have this, we're now going to plug in. Here, I'm going to call this equation 1, equation 2. Plug into 1. I'm sorry, 2, I mean. Sorry. That's x2 prime is equal to x1 minus 2x1 prime. And then we have a 2 times 2 in here. So that's minus what, 4? X1? Yes. And then, now what do we do? Now remember, okay, so this is a little weird. I'm going to rewrite this and you'll see why I'm doing this in a second here. I plugged in for x2. I plugged back in for x2 prime. Uh, okay, yeah, this is the weird part right here. So let me explain this better. Yeah, so this is pretty weird. What I did, let me just clarify this. Plugged. So what you do is you solve for one of the okay, so this is what you do. We have x1, we have equations for x1 prime and x2 prime. You want to isolate, you want to isolate either one of them to be in terms of x1 or x2. After you do that, you then plug the equation, the original equation for x1 prime or x2 prime back into that new equation. So now I'm plugging x2 prime back in, because we know that this is equal to x1 minus x2, 2x2, right? So, where am I? Why is that prime? Oh, I see. I'm sorry. You you use plug in x1 prime from equation 1. So if you look at equation 1 here, right here, let me get my pointer out. We solved, here's equation 1, we solved for x2, right? Rearrange it for x2. This is a different x2 prime. So we took this x2 and we plugged it into number 2 here, which is right here. That comes from this equation. This, from this equation, needs to be solved. So you plug this x2 prime in for x2 prime here, and you get this is equal to this from the equation. So now that we have that settled, what can we do? First of all, you'll notice here that I only plugged in x2, so we still have to take the derivative of this equation here. Because I forgot, you know, this is x2 prime right here. So now we take the derivative of this, we have x1. Oh no, that would be what? That shouldn't be an x2 prime, is it? What is that doing in there? That's an x1 prime. Plus 2xi, that's this right here. Okay, that's x1 double prime plus, oh, that should be minus 2. Wait, what am I doing? Oh, no, that's plus. Plus, sorry, I'm losing my mind right now. Plus 2x1, yeah, okay. And that's still equal to x1 minus 2x prime, x1 prime minus 4. That's an x1, I believe. That's an x1. From here, we can rearrange. We can see that these, oh no, those will add together. So we have x1 double prime plus 4x1. No, wait, no, that comes over, no, that's 6x1, right? Something ain't right here. Something ain't right. So, okay. We have 2 x1, x1, and negative 4. That is 2 plus 3. Oh wait, I forgot to take the derivative of this over here. That's completely my fault. Jeez, okay, that's plus 4 x1 prime, and then we get this minus 3 over here, so this becomes plus 3 x1. That's equal to 0. Now we have our ODE, right? So we've completely, so we've solved the first differential equation for x2. We substituted the result of a into the second differential equation, obtaining the second order differential equation for x1. Now it wants us to solve the differential equation found in b for x1. So now you have to go through here and you gotta solve the characteristic equation, right? Solve for the characteristic equation. So remember, it's just substitute x equals e to the rt. That result leads to r squared plus 4r plus 3 equals 0. You then get r plus 3. That would be plus, I think that should be r plus 1, yeah, equals 0. So then that tells you that r is equal to -3 and -1. Well, I guess I'll call this r1, r2. So then x1 is equal to, remember we read our general solution, c1 e to the -3t plus c2 e to the t. Using this, we can solve for x2. Remember, we know that x2 is equal to x1 prime plus 2x1, as seen up here. We plug x2, well no, we plug x1 into here. So in order to do that, we need x1 prime. So x1 prime would be -3 c1 e to the -3t minus c2 e to the t. Pretty simple, right? So then we just plug that right into x2 here. That is -3 c1 e to the -3t minus c2 e to the t plus 2 c1 e to the -3t plus 2. Remember, I'm now on this term over here. Plus 2 c2 e to the t. This probably simplifies. Yeah, so this definitely simplifies. x2, that would be -3 plus 2 is -c1 e to the -3t. That is plus c2 e to the t. So here's our first one of our equations for x2. Here's our equation for x1. And that's the solution. We have our, we converted it back. Where is it? So that is the way that we solved for x1 and x2 using the first method, right? The easier method that we will get into is actually solving for the eigenvalues and eigenvectors, and you get the answer in matrix form. You'll get this exact answer. You get x1 and x2 in matrix form, which we'll get to. It's a lot easier than doing this. This can be a little weird because of the way you have to plug in stuff. That's why it actually tells you right here exactly what to do, because it could be a little tricky. Let's take a look at one more question here. Maybe I'll do 2 of them down here. We'll see how fast number 7 takes. Let's look at number 7 here. I think it's the same thing. Yeah, so it wants us to transform the given system into a single equation, same thing. Find x1 and x2. And sketch the graph of the solution. So this is getting a little bit all over the place. So what I want you to think here, look back at this one here. Imagine taking a second order ODE, converting it into this system, and then using the eigenvalue method to get the solution, right? That's the most intuitive way to do this. This is telling you if you get a first order equation, this is the solving it the other way. This with method 1, you have to take this, you have to actually put it back. The only way you can solve it without the eigenvalues is you have to take it back into second order and then solve it the way we know how to do it. That's the only way to do it that way. That is not very good. That's not a viable way to do it if we're doing, control systems analysis or stability or, just that stuff in general. We can't do that. So we have to eventually learn this eigenvalue method. Take the second order term, into first order, or if they already give us the first order like this one does, that's even better. Okay, so let's look at number 7 here. They give it to us. It wants us to do it the old method way, so we're going to look at method 1 again, where we convert it into a singular equation of second order, and then we can find x1 and x2. Oh, we have initial conditions now. Interesting. Yeah, so this is going to be a little bit longer. So, okay, number 7 here. This is probably the only one I'll do because I think they're all the same. Let me just double check quick. Yeah. They're all the same. You know, one of them. It's a number 7 here. It is. You can try these on your own. It is just a normal. For second order, it's just a normal. There's a 2 defined roots. Let me see here. Yeah, just a normal unique root to the characteristic equation. Number 8, I think, is complex. Yeah, number 8 has complex roots. You guys know how to solve the second order with complex. And then number 9, let me take a look here. That one is also complex. That one looks pretty difficult. No, it's not that bad. But you guys know how to solve all of these. You know, it's just a matter of reviewing your old second order methods. So I'll just do number 7 and call it a day. Okay. This one, oh yeah, this is a little lengthy. Okay. So we have x1 prime equals 3x1 minus 2x2. We're going to rewrite this for x2. We're using the same method. I'm going to rewrite this one for x2. Negative x1 prime over 2 plus 3x1 over 2. Remember, we're going to need to use this later again. Excuse me, x2 prime is equal to 2x1 minus 2x2. Let's plug this in to here. As x2 prime is equal to 2x1 minus 2, and I'm out of space. I should have thought about that. Minus 2, where was I? X2, so that's minus x, that's plus x1 prime. All right. Let me double check this. 2x1 plus 2, yeah, x1 prime minus 6. Let me think about that. That's what, 2 times 3 is 6 over 2. So that's 3 x1. Now we plug in, we solve for x2 prime using the one we solved from the first order. I'm going to go right ahead and take the derivative immediately. That is negative x1 double prime over 2. I'm looking at this right here. Plus 3x1 prime over 2 is equal to 2x1 plus x1 prime minus 3x1. Let's rearrange that. What can we solve for here? x1 double prime, right? This would be the x1 double prime second order equation. So let's reduce this. So we can multiply everything by 2. Actually, I see some things that can be simplified initially. So we have negative x1 double prime over 2. This term here and this one here can be rearranged. 3 over 2, let me think about this, plus 1 would be that is 5 halves. So we have, actually it's minus 1, so that's 1 half. So that's plus x1 prime over 2 is equal to, that's just minus 1, or minus x1. Multiply everything by 2. I'm going to multiply the negative through. This is x1 double prime minus x1 prime. I'm going to move this over. That becomes positive. You multiply it by a negative. 2x1, negative 2, equals 0. Solve the characteristic equation. Remember, in case you guys forgot, in case you're like, where did he get that from before? x, well, if you say this is e to the rt, x1 prime is equal to r e to the rt, x1 double prime is equal to r squared e to the rt. You plug all these in. R squared, you should remember this from first order stuff. These cancel. You're left with r squared minus r minus 2 equals 0. Solve the characteristic equation. This is our characteristic equation. We solve it. R minus 2 times r plus 1, right? Equals 0. Then we get r equals 2. I say that's r1. This is r2, negative 1. So then x1 is c1 e to the 2t plus c2 e to the negative t, right? We know how to do this. Now, this is where we're going to plug x1 back into, where would we plug this back in? I guess back into x1 prime, right? This up here. Wait, what was I doing here? Hold on a minute. Okay, so looking at this one up here, we have to actually plug it back into the one that we originally solved for. So it's not the equation 2, it's going to be the one that comes from equation 1. So we solved, okay, so it has to go back into this one here. Well, that's annoying. That's annoying. So it has to go back into this one here. By the way, I'm doing this problem without looking at my notes. That's why I'm able to do this a little bit faster. That's why I'm going faster. Okay. So x1, so I already forget what it was. Negative x1 prime over 2. Prime. Oh god. Okay, so we need to find the derivative of this first. That's easy. Right? So then we have negative x1 prime over 2. So that what is that? x2 prime, x2 equals negative x1 prime over 2. Divide this by 2. Negative c1 e to the 2t minus c2 e to the negative t. That'll be over 2. We have the other term, minus 3x1. x1 minus 3c1. Oh, come on. E to the 2t plus 3c2 e to the negative t. Is that a t? Okay. There's our x2. That can be simplified. That is negative 1 minus 3. Alright, did I do this right? Shouldn't this be divided by 2? Oh, plus 3x1 over 2. Okay. Easy fix. We're fine. I need to do this math in my head here. So this is negative 2 over 2 minus 3 halves. I need to write out the math for that stuff. x2 would be, what's that? Negative 5 halves. Or is it 5 halves? Isn't that? Why do I have positive? Why is that negative? Minus 3x1. Is that plus? Did I write something down wrong up here? That becomes negative, then it becomes positive. No, that's right. What the hell? Apparently both terms are positive. Even though they're not in... Oh, I'm just plugging in x1, right? Oh, the second term's positive. Oh, what am I doing? That is plus. What am I doing? Oh my lord, okay. Negative 5 halves. No, it's not negative 5 halves. Now it's plus. That's a negative 1 half. So that's a negative C1 e to the 2t over 2. That's positive 1 half. Sorry. That would just be C2's. That's just 1. That's just C2 e to the negative t. Goes with 3 over 2 minus 1 half. That's 2 over 2. That's 1. Yeah. Okay. I've come to realize something here. We plug this into a negative x1 prime, meaning this term here has to be positive, so I once again messed that up. That was bad. See, I am really out of practice. I had not done this stuff since I last made those videos, and that was like over a year ago. That was almost a year and a half ago. So it's been a while. So bear with me. After this, we won't have to look at this again, I don't think. All right, plus C2v to the negative t, because we'll know our nice eigenvalue method. Where was I? I'm spending way too much time on this. Okay, yeah, this is now plus 2 because you have 1 half plus 3 halves. That's 4 halves, which is 2. We have x2. But now, we're not done yet. We have x2 and we have x1. Let me rewrite them. And we have our corresponding initial conditions that were given, right? So, which one was given for this one? x1 of 0 equals 3. And x2 of 0 was 1 half. Okay, so now we just solve, with the initial conditions. We set, we set t equal to 0. I'll do this one on the left first. Let me do this. Put a line down the middle. Come on. Thank you. Let's solve for x1 here. Well, no, let's solve for the. So this is 3 equals c1. Remember, e to the 0 is always 1, so it's c1 plus c2. And then we have this one over here. Okay, I'll get rid of that line. I just realized we need to solve the system. We have 1 half equals, once again, c1 over 2 plus 2 c2. Okay, now we just solve for c1 and c2 of the given system. I'll call this equation 1, this equation 2. Let's rearrange this for c1. That's 3 minus c2. 1 half. I hope I get the same answer as I have on paper here. That's c1. That's 3 halves minus c2 over 2 plus 2c2. It's an arrow. Okay. This becomes 1 half minus 3 halves is negative 2 over 2, negative 1. This is minus 1 half c2 plus 4 over 2 c2. That would be 3 halves. That's negative 2 over 3 is equal to c2. Is that what I have here? Yes, it is. Beautiful. Plug that back into c1. c1 is equal to 3 minus negative 2/3. That is equivalent to 9/3 minus negative. That becomes plus 2/3. Like minus, what am I doing? Okay. That's 11/3. That is correct. Fantastic. Then we can rewrite x1 as 11/3 e to the 2t. This was minus, right? No, just plus c2. So plus, yeah, that's minus 2/3 e to the negative t. x2, c1 again. Is that negative or positive? They're both positive, so that this is divided by 2. So it becomes, yeah, that's why the 6 is there. Okay. Sorry, I was copying off my notes. This is divided, oh, this is times 2, so yeah, that's 4/3. And this is the solution to that problem. So that was really ugly. Took a long time. I'm a little out of practice on that stuff. Sorry about that. This is the end of this video. As you can see, a quick little recap. We learned how to convert a second order ODE into a system of 2 first order ODEs, which is very common in physics, in the world of physics. Remember that these are necessary. It's necessary to do that to understand system stability of a system, to better understand the fine print of the system. Like, for example, if you have a system of multiple variables, say position and velocity, you want to be able to understand how, well, you can have, this is so hard to explain because you can have, let's do this. You have position and you have angular rate. You have an angle and position. 2 degrees of freedom. Let's say you have an equation, a second order equation that has x double prime, right? But you want to solve for x and x prime, right? You have to convert it into a system of x. You get one equation of x, one equation of x prime. But now, if you have 2 degrees of freedom, you'll have 2 equations that you have to convert into state space, or as we call it, just converting to first order system. So then you'll have you'll have 4 total equations, one for position, one for the angle, and then one for the rates of the position and of the angle. Those 4 equations give you a lot more information than the one equation tells. That's why we want to do this. So now in the next few videos, we have to prepare ourselves to now make our lives easier in the long run by learning a little bit of matrix. I'll do some matrix review. Actually, I'll show you my order here, my layout. We're going to do matrix operations, and then row reduction. Then we're going to look at linear independence, and then we will do eigenvalues and eigenvectors. And then we'll get into some real fun stuff. Let me tell you, real fun stuff. But yeah, that's the end of this video. I hope you enjoyed. See you next time for matrix operations.